Welcome to Episode 40, VMs, Containers, Microservices, Serverless, where we unpack the major compute abstractions that shape modern cloud architecture. Each represents a distinct level of control, automation, and operational complexity. Virtual machines mirror traditional infrastructure in the cloud. Containers introduce portability. Microservices refine modular design, and serverless abstracts infrastructure entirely. The challenge is not choosing the newest option, but selecting the one that best fits workload behavior, team skill, and business goals. By understanding the trade-offs between flexibility and simplicity, stability and speed, you can match the right abstraction to the right job. This episode compares these models plainly, helping you align architecture decisions with measurable outcomes instead of technology trends. Virtual machines, or VMs, offer maximum control but carry operational overhead. They emulate full hardware stacks, including operating systems, making them ideal for legacy applications or specialized configurations that require custom kernels or drivers. VMs provide isolation and predictability, with users responsible for patching, scaling, and monitoring. For example, a regulated financial system with strict compliance requirements may run on VMs to preserve consistent environments. The advantage lies in compatibility. Nearly any workload can run unchanged. The trade-off is effort. Every update, dependency, and backup must be managed directly. VMs remain relevant as a bridge for modernization, allowing migration without code changes while gradually introducing automation and managed services over time. Microservices elevate architecture from packaging to design philosophy. Instead of one large application, functionality is divided into small, independently deployable services that communicate through APIs or event streams. This separation increases flexibility. Teams can develop, test, and release features independently. For example, an e-commerce platform might have services for orders, payments, recommendations, and shipping, each scaling according to its load. Microservices enable resilience. If one component fails, others continue operating. Yet this autonomy introduces complexity. Network latency, distributed tracing, and versioning must be managed carefully. Observability and disciplined governance become vital. Microservices succeed when paired with strong DevOps culture and automated pipelines that coordinate integration without central bottlenecks, turning organizational agility into a technical reality. Serverless computing represents the furthest abstraction, removing all infrastructure management. Developers deploy code or containers that run automatically in response to events, scaling instantly and charging only for active execution time. Google Cloud offers Cloud Functions and Cloud Run for this model. Serverless systems suit unpredictable or bursty workloads like webhooks, file processing, or API gateways. For example, an image processing service might scale from 0 to thousands of executions per second during peak uploads, then scale down completely when idle. The benefits are simplicity and cost efficiency, but trade-offs include cold start delays and less control over runtime environment. Serverless enables high developer velocity and low operational burden, making it ideal for modular, event-driven systems that value flexibility over permanence. Development velocity differs across these abstractions. VMs require extensive provisioning and manual configuration before deployment, slowing iteration. Containers standardize environments, enabling faster testing and integration. Microservices push velocity further by allowing parallel development, though coordination between teams becomes critical. Serverless offers the fastest deployment cycle. Upload code, define triggers, and deploy instantly. For example, a marketing campaign API can launch in hours on serverless, but might take weeks on VMs. Each model balances speed against complexity. As velocity increases, so does the need for automation, testing, and observability to prevent chaos. The right choice depends on whether you prioritize time to market, stability, or customization. Fast does not always mean sustainable. Scaling behavior defines how these models handle growth. VMs scale through instance duplication or resizing, which takes minutes. Containers scale in seconds through orchestration platforms that add or remove pods based on demand. Microservices inherit this scalability by distributing load across specialized services. Serverless scales automatically, handling thousands of concurrent requests without pre-configuration. However, serverless may experience cold starts, the brief delay when initializing new instances after idle periods. For example, a real-time analytics pipeline might prefer containers for predictable throughput and lower latency, while sporadic workloads like invoice processing favor serverless. Understanding scaling characteristics ensures you meet performance targets efficiently, matching elasticity to actual usage rather than theoretical capacity. Observability changes with each abstraction. On VMs, monitoring focuses on system health, CPU, memory, disk, and uptime. Containers add layers like cluster metrics, resource utilization, and log aggregation per pod. Microservices require distributed tracing to follow requests across services and correlate failures. Serverless emphasizes event-level monitoring, execution counts, and latency metrics from cloud dashboards. For example, tracing a payment failure in a microservice architecture requires linking logs across APIs and queues, whereas a serverless function logs per invocation. The more distributed the architecture, the more critical centralized observability becomes. Investing in metrics, structured logs, and correlation IDs transforms complexity from chaos into insight, maintaining reliability as systems scale and diversify. Security boundaries and patch responsibilities evolve as abstraction increases. With VMs, users manage everything, from operating system updates to network firewalls. Containers shift responsibility to image scanning and runtime isolation within shared clusters. Microservices require secure APIs, identity tokens, and encryption between services. In serverless environments, the provider handles patching and infrastructure security, leaving developers responsible for secure code and permissions. For instance, a containerized environment must track base image vulnerabilities, while a serverless setup primarily manages IAM policies and data encryption. The rule of thumb: the more managed the service, the smaller your patching surface, but the greater your need for configuration discipline. Shared responsibility changes, but accountability remains constant. Cost profiles differ based on usage patterns. VMs incur constant cost for allocated resources, even when idle. Containers optimize resource density, but still bill for active infrastructure. Microservices spread costs across multiple deployments, making governance crucial to avoid sprawl. Serverless introduces pay-per-use pricing, charging only during execution, which suits variable or unpredictable loads. For example, a financial batch job running daily benefits from serverless economics, while a 24/7 analytics engine may find VMs or containers more economical. The key is matching billing models to workload rhythm. Predictable, long-running systems prefer reserved instances. Intermittent tasks thrive on event-driven models. Awareness of cost behavior ensures you optimize spend without sacrificing performance or flexibility. Team skills and operational readiness influence which abstraction succeeds. Teams experienced with system administration and compliance may favor VMs for control. Developers familiar with DevOps pipelines gravitate toward containers and microservices, where automation and collaboration drive efficiency. Serverless demands software engineering discipline, clear function boundaries, stateless design, and monitoring for ephemeral workloads. Training and documentation close skill gaps, ensuring teams can manage complexity responsibly. The ideal progression builds maturity gradually. Start with familiar control, add automation, adopt modularity, and finally embrace event-driven patterns. Architecture is as much about people as technology. Alignment between team capability and abstraction level determines reliability and sustainability. Migration paths connect these paradigms as organizations evolve. VMs often serve as the first step. Migrated workloads run unchanged, buying time to modernize. Containers follow, improving portability and efficiency. From there, applications can be decomposed into microservices for flexibility, and critical functions can transition to serverless for agility and cost efficiency. For instance, a monolithic web app on VMs might first move into containers, then split into microservices, and later offload background processing to serverless. Each stage builds on the previous one, preserving stability while introducing modern practices. Migration is not about jumping directly to serverless, but about progressing deliberately as systems and teams mature, balancing ambition with continuity. Choosing between these compute paradigms should depend on product needs, not fashion. Trend chasing leads to over-engineering, while thoughtful alignment ensures lasting value. For latency-sensitive workloads, low-level control on VMs or containers may be necessary. For rapid iteration and unpredictable demand, serverless may be optimal. Microservices suit complex systems that require parallel evolution, while monoliths may still outperform when simplicity matters. The best choice is the one that meets requirements reliably, scales sustainably, and fits team capability. Technology should amplify goals, not dictate them. Selecting deliberately avoids both stagnation and churn, grounding architecture in purpose rather than novelty. Aligning architecture with outcomes is the essence of modern computing strategy. Each abstraction, VMs, containers, microservices, and serverless, serves a role in the continuum between control and convenience. The journey is rarely all or nothing. Most environments blend these models, using each where it excels. Modern architecture is about right-sizing, not revolution. When decisions follow clarity about performance, scale, cost, and culture, technology adapts gracefully to business change. By understanding each abstraction's strengths and responsibilities, teams design systems that evolve smoothly, balancing innovation with stability. The goal is timeless. Build what serves your mission best today and tomorrow with confidence in every layer of the stack. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.